Good morning, everyone. During last class, we have seen the introduction to boiling, boiling types, and boiling regimes. Boiling regimes consists of three different phases depending on the increase in excess temperature, which is surface temperature minus saturation temperature. And they are interface evaporation, nucleate boiling, film boiling. Now, we will see uh, the one of the problems. Just we will solve one problem, and we have seen what is critical heat flux. The point of maximum heat on the boiling curve, the point of maximum heat flux on the boiling curve at which transition from nucleate boiling to film boiling initiates. Just it changes, the curve changes its direction. The point at which the curve changes the direction, or the boiling the nucleate boiling type gets converted to the film boiling, and that point is called as critical heat flux. And I have already insisted you to go through the data book to find out the correlations regarding nucleate pool boiling, critical heat flux for nucleate pool boiling, and film pool boiling. Now we will move on to see one problem. Water at atmospheric pressure is to be boiled in polished copper pan. Water at atmospheric pressure is to be boiled in polished copper pan. The diameter of the pan is 350 mm and is kept at 115 degrees Celsius. The diameter of the pan is 350 mm and is kept at 115 degrees Celsius. Calculate the following. First one, power of the burner, rate of evaporation in kgs per hour, critical heat flux for these conditions. Critical heat flux for the given conditions. So what is given? Now the given things are atmospheric pressure. We know 1 atmospheric pressure is equals to 1.01325 bar, and at that pressure the water is to be boiled in a copper pan, and at atmospheric pressure the saturation temperature of water is 100 degrees Celsius. We know it. So if the pressure is given differently, say 3 bar or 3 atmospheric pressure, you need to go through the steam table and at the given pressure what is saturation temperature. That is what we need to record. Here we know for 1 atmospheric pressure the saturation temperature is 100 degrees Celsius for water. So there is no problem there is no abnormality, there is no critical thing to think about. But if the pressure is different, you must observe what is the saturation temperature. It may be 150 degrees or 130. It will vary from 100 degrees Celsius depending upon the pressure. Now, the pressure is given and we know the saturation temperature is 100 degrees Celsius. The pan diameter is 350 mm and is kept at 115 degrees Celsius. The temperature of the pan surface is 115, which is greater than the saturation temperature of water at 1 atmospheric pressure. And further he is asking us to calculate the following. See, the power of the burner, rate of evaporation, critical heat flux. These three things is what we need to discuss. Now there is a small note. According to the boiling regimes, on x-axis it is excess temperature, y-axis it is heat flux. Depending on the excess temperature variations, the regimes are decided here. One is, we know the three regimes: interface evaporation, nucleate boiling, film boiling. There are three things. These three are distinguished with respect to water at 1 atmospheric pressure. It is delta TE, excess temperature, T saturation minus, T surface minus T saturation. If it is 5 degrees Celsius, that will come under interface evaporation zone. If the excess temperature, if it is in between 5 degrees to 50 degrees Celsius, it is a nucleate boiling. And 50 to 150 degrees Celsius is film boiling. Yes, film boiling. Now, so under what category the given problem will come under, the boiling is coming under, that we need to see. Simple. The surface temperature minus saturation temperature. Surface temperature is 115 degrees Celsius minus saturation is 100 degrees Celsius is 15 degrees 15. This 15 degrees Celsius is in between 5 and 50, 5 and 50 degrees Celsius, and the type of boiling is nucleate boiling zone into which it is coming. Now, the most weapon for our heat transfer subject is data book, the biggest weapon. Now we need to open our data book. Under nucleate boiling type, whatever the relations are required according to the given problem. Say, power of the burner is asking, rate of evaporation, critical heat flux is asking. So these relations must be taken, or if anything need to be calculated, depending upon the relations that we know, we need to do it. Now, the correlation from the data book is taken for heat flux. So heat flux is coming under the critical heat flux, third one. Let us see what is done in this problem. Now, heat flux QS is equals to null H of G into rho L minus rho V by sigma into, power 0.5 into bracket open CPL delta TE excess temperature by CSF H of G Prandtl number power n whole to the power 3. This relation is taken from the data book. The liquid and vapor properties must be chosen or taken at 100 degrees Celsius, which is a saturation temperature. This point we need to remember. Whatever the properties that were given in the correlation for heat flux, U is equals to nu L H of G, that relation is there. So that equation 1, the properties in equation 1 must be chosen or selected from the data book at 100 degrees Celsius, which is a saturation temperature. At saturation temperature, we must take the properties, select the properties from the data book and convert them into suitable, what we call it as, convert it into proper number dimensions, and according to that we need to substitute. Now we'll continue it. See, at 100 degrees Celsius only these properties were taken. Rho L, the densities were taken, specific heats were taken, dynamic viscosity is taken, Prandtl number is taken, H of G, that is latent heat, H of G, amount of heat required, the enthalpy change during the conversion of a fluid from liquid phase to a gaseous phase, it is 2257 kilojoules per kg. They all are specific. Now the important thing we need to remember is also N is equals to 1 for water, N is 1.7 for other fluids. It is also a given thing, already pre-existing thing. Experimentally they have calculated. It's a type of dimensional analysis. N is equals to 1 for water, N is equals to 1.7 for other fluids. And sigma, which is surface tension, again you need to take it at 100 degrees Celsius. And like specific heats, we need to take everything from the data book. Now, after taking that, you substitute these properties in QS and you calculate. We will get it as 471.06 kilowatts per meter square. And heat flux. What is heat flux? Kilowatts per meter square. Heat flux is the amount of heat traveled or transferred per square area, per area. So square meters means it is 471.06 kilowatts per meter square. It is given. Now, which is heat flux. So Q by A is equals to 471.06. Now we substitute, we get we substitute area and we get what is heat. Q is equals to 471.06 into pi by 4 d square. What is diameter? We know the diameter of the pad is 350 mm. Convert it into meters and square it. You will get pi by 4 d square. And Q is equals to 45.32 kilowatts. And so this is what the rate of heat, the power supply must be 45.32 kilowatts. Next, rate of evaporation, m dot. What is the rate of evaporation? Q is equals to m dot HFG. This is the basic formula. We know this relation. We know Q is equals to m dot into HFG, because Q, whatever Q we found is it is specific. The Q we found above is specific. Now, because HFG is kilojoules per kg. Per kg means it is specific. Now, when you substitute, when you multiply with m dot into HFG, then we'll get what is mass flow rate. M dot is equals to Q by HFG. We get 72 kgs per hour. We get. And the third one, critical heat flux. For critical heat flux, again the relation should be taken from the data book. It is 0.18 HFG rho v. Same that from the data book you need to take sigma is surface tension, G acceleration due to gravity, rho L density of the liquid, density of the vapor is rho v by rho v square, and these properties should be taken at Ts plus T saturation by 2. Surface temperature plus saturation temperature by 2. This is different in this case, the critical heat flux. And we get the final answer after substituting these properties in the correlation Q critical. We get 1.52 into 10 power 6 watts per meter square, or 1.52 megawatts per meter square. So this is how we use our data book and we solve the problems. And in the next session we just try to go through this problem, try to understand the terms, open the data book. Just once you solve this, then same thing, similarly you can solve the problems in other topics also, like in condensation also you may get problems, and the same procedure is used. So go through it, and in the next class we will see what is condensation, and we will complete this condensation by the next class, and we'll enter into the radiation. Thank you.